Hello everyone, welcome to video 7 of chapter 3. In this video, we begin our study of chapter 3.3, that is an introduction to the simplex method. The simplex method is the main method that we will learn to solve linear programming problems. It's a rather detailed method with many steps, and there are many different situations to consider. So in order to give an introduction to it, we will go through an example and explain how to solve it, and along the way of solving them, and we'll explain the ideas involved. Okay, let's get started. We will consider a problem in standard form. We have learned about that already, so we will be looking at a minimization problem of a linear function, that's the objective function, which is set to be z. So z is the amount we want to minimize, and we call this objective function equation star. The whole thing is subject to a set of constraints. So here we have chosen to have two constraints, which we listed as 1 and 2. And taking a look at the constraints, we see that these are all linear functions of the variables on the left-hand side and a constant on the right-hand side for both constraint 1 and constraint 2. Okay, you might pause the video for a second and take a closer look at the whole problem setting. Okay, and we are so we have seen this type of problem already in many examples we have had. Okay, so through this chapter 3.3 here, we will talk about this problem in a lot of detail about how to solve it and about various issues involved, and then we'll try to generalize those observations and hopefully understand a general algorithm. Okay, so let's get started. So the first step, we know from the discussion in the previous section, we know that we need to put the constraint in a canonical form. So not only that, there are also restrictions in this. So what do? So we need to choose two basic variables among all the variables. We select it, and this choice, after we did the pivoting and after we obtain a basic solution, we should have a feasible one. So the basic solution should be a feasible solution. Okay, so that is the first step. Okay, so this step, we have done this kind of a computation to rewrite in canonical form for some examples, and we have known that if you are not careful, you just pick two basic variables, you could end up in a basic solution that is not feasible with the negative component. Okay, so I want to say that this step here, pay attention, it could be a major difficulty in general. It's not that trivial. Okay, but let's try to work this out for the example we have at our hand. So let's recall one technique or method we have learned along the way, that is the geometric interpretation of this. Why can we use that? Well, it's because this problem we have here are with only two constraints, so we can rewrite it using vector notation, and same as the previous example we have done. So we pull out x1, x2, the variables out, and we collect the coefficients and put them in the vector. Okay, and the right hand side is here. So basically this is the same as the constraints. Now it's rewritten in this specific form. Okay, and we also know that I didn't write this out, but we know we call this vector v1, this vector v2, this v3, this v4, and this v5, and this is vector b. That was our notation. Okay, so now I have a claim. You have noticed that I highlighted v2 here and v3 here. They are in color. So I claim that I could use x2 and x3 as the basic variable, and it will give me a basic solution that is feasible. Okay, so from our discussion, we know in order to verify that, we need to show that the vector b here on the right hand side can be written as a linear combination of v2 and v3 with non-negative coefficients x2 and x3. What we need to do is to draw the vector v2 and v3, and then to see that if the vector b lies between the wedge of these two. So let's do some drawing. Okay, so here is the drawing. So x2, 0, 1, and then it's the vertical axis, so the green is corresponding to that green. And now v3 here is 1, negative 1, so 1 in horizontal direction, negative 1 in the vertical direction, so it's pointing down with slope negative 1. And what is the b vector? Well, 6, 9, they're both positive, so it's pointing with the upward slope. Now we see that v2 and v3, the wedge between them, and the angle that's less than 180, this wedge here, the gray area, actually include the b vector. And that's why this choice is good, okay, because now b can be represented by a linear combination of v2 and v3 with non-negative coefficients, which will be the value of x2 and x3. Okay, so this you can actually easily do it by sketching these vector, the direction of them in the plane, and look at the vector of the b and to see between which two vectors this b would lie in, and then you could choose them as your basic variables. Okay, so here is a way for you to select the basic variables. Now, once the basic variables are selected, then we would need to go through a pivoting process. Okay, so let's look at x2. We see that in equation 1, x2 is not there. And in equation 2, x2 has coefficient 1. So if we take this x2 in the second equation as our pivoting point, then we see that it's actually ready and there's nothing to do. So this comes for free. After that step is cleared, now we need to pivot x3 in the other equation, and namely in equation 1. So this is colored in red. We need to pivot that. And remember, the goal is to make a coefficient 1 here, which is already okay, and make this x3 disappear. So you could simply add x1 on top of x2 and replace x2 with that, and then this will be gone. Okay, so it's a simple step of pivoting. Okay, so we have done that exactly. So now the x3 is not here, and the coefficients here are adjusted accordingly by adding these on top. You can verify that this is correct, and then this will be the new system of equation for the constraints in canonical form with the basic variable x2 and x3. Okay, so once that pivoting step is done, then we can write out the basic solution. That is, all the non-basic variables are 0, so x1, x4, x5 are 0, and the basic variables will be taking the value on the right-hand side, right? So x2 here is in equation 2 will be 15, and x3 occurs in the equation 1 will be 6. Okay, so we can write it as 0, which is x1, 15 is x2, 6 x3, then this is x4, and this is x5. So it's a more compact way of writing the basic solution. And nothing is negative, so this is feasible. Okay, so now I put the new equations for the constraints here. So now our problem is minimizing this objective function, which we haven't touched, subject to the constraints, which are now in canonical form, with the basic variables x2 and x3. Now we go to the second step. Step 2, what we do is the goal is to rewrite the objective function also into the standard of the canonical form. So we want to write it in terms of non-basic variables only. Okay, we want to eliminate the basic variables. Namely, we want to get rid of x2 and x3 in this equation. There are various ways of thinking of doing that. One could say, let's say if you want to get rid of x2, then you could write x2 in terms of everything else from equation 2 and plug the expression in, and then you do it for x3. But there is another way of doing it, more in the same spirit as pivoting. Let's explain. Okay, we can change our way of thinking to think that we have 3 equations, 1 and 2, and equation star. And now we want to remove, let's say, x2 in the equation of star. So what we could do was taking this equation 2 here, we can multiply by -1 and then add on top of that. And then the x2 will be gone. It has the same effect as expressing x2 in terms of others and substitute in it, but probably is computationally faster. Okay, and once we have done that, let's say multiply by -1, so this is +3 at -4, you get -1, x2 becomes 0, that's just the way we manipulate it, x3 is unchanged, and this is -6, add on top of 7, you get x4, and then -3 on that, it happened to be 0, and then the right hand side z, and then I have -15 coming from here. Okay, and now the star becomes this one, we write it star prime. Once you have seen how this step works, you could adopt the same idea and get rid of x3 in here. Okay, let's look at it. Now we want to remove x3 in this equation star prime. Then we can utilize equation 1 prime, which has an x3 here. We can multiply this by -1 and then add on top of that. Okay, so if we do that, then we get -6, add on -1, we get 5, and then there's no x2, and that's 0, so this is still 0, and then this x3 become -x3, cancels that, it becomes 0, and this is 2, add on top of 4, I get 3, and this is -2 on 0, it's -2. And then I have -6, add on top of that, I get -21. So now this objective function becomes this. we would drop this term and this term because they're 0, and you see that now z is expressed in terms of x1, x3, x5. That is the non-basic variables. Okay, after the step, now let's summarize what problem do we have. Let's write it out. Okay, so now we have the following problem. We want to minimize z with the following. So we write it in this form. So pay attention. This way of writing will be rather standard from now on. So we write that's the first constraint and that's the second constraint. The first two equations are the set of constraints that we have, and then we manipulate it into canonical form with x2 and x3 as the basic variable. And the basic solution takes the value on the right-hand side, which are positive. Okay, and the last line, which is labeled as star double prime, that is the equation for the objective function. That is, the value z is expressed here in terms of the non-basic variables. Note that we get rid of them here and here, the two basic variables, by actually a pivoting process, treating this as an equation in the whole setting. Okay? So you can pause the video and take a look and think a bit about what we have done and then how we achieved this expression. Okay, so now we know if we have things in this expression, this linear programming problem, and satisfy the definition of the canonical form of a linear programming problem. Okay, so once it's expressed in a canonical form, then it is very easy to find out the basic solution and the optimal value. So we know the basic solution, which is feasible here, is to set all the non-basic variable to be 0. So x1, x4, x5 will be 0. So these three are 0. And then x2 and x3 will equal to the corresponding right-hand side. So 15 for x2, which is here, and then 6 for x3, which is here. And at this solution, what is the value of z? Well, you know x3, x4, x5, they will all be 0, right? So the left-hand side here will be 0. So z would equal to exactly the negative of this quantity, okay, which is 21 here. Okay, so I just want to call your attention to once you get the canonical form, how can you quickly write out the basic solution which is feasible, where to get the numbers, and the value of the objective function, where to get the numbers. So in particular, pay attention. It is the negative of this which is your z value. The reason is that everything here is 0. Okay? All right, so that is the first step and the second step. And then once we have expressed the problem into this canonical form, then comes the heart of the matter of the simplex method, which we will explain in the next video. So hope you enjoyed this, and I will see you next time.